Y3E Electric Field. We first consider fields. In physics, physical quantities are, for example, mass of a single particle is a fixed number. However, usually, for example, electric field, magnetic field, gravitational fields, there are various fields. Fields is a physical quantity that is a function of position. So it has different values depending on the position. In addition, it may depend also on time. It depends on time too. We call it time-dependent field. Otherwise, it is a time-independent field. For the time being, we consider electrostatic case. Electrostatic means the charge distribution does not change depending on time. It is independent of time. So we consider for short time, time-independent field only. The temperature, for example, is also field that differs by position. However, a temperature has only a single value at a single point, then means it does not have any direction. So temperature and pressure, such kind of field is a scalar field. Electric field has its own value with direction and magnitude. The gravitational field too, they are vector fields. Electric field denoted by E as a function of position x is defined in terms of the electrostatic force, that is Coulomb force, divided by the test charge. Test charge is a charge, small charge q. It is infinitesimally small mathematically. However, we know the elementary electric charge is E, that is a finite number. We assume that it is negligibly small. So the reason why we choose a test charge as an infinitesimally small charge is to do not let this test charge modify the electric field surrounding that charge. So for example, we have capital Q at the origin, then electric field will be generated, and the definition of the electric field is electrostatic force between these two charges divided by the net charge of the test charge. The SI unit of the electric field is Newton per Coulomb because force divided by the electric charge. The electric field is independent of the test charge, we assume. Electric field lines. Michael Faraday introduced the field lines, especially for the magnetic field lines. Electric field lines extend away from positive charge and toward the negative charge. So if we have many charges, electric field, so field lines are being emitted from the positive charge. If you have two plates, positively charged plate and negatively charged plate, then the electric field lines shows this direction, for example. Electric field lines extend away from a conducting sheet along the normal. Point, radial, and surface it is perpendicular, so it is normal to the plane. If it is a straight line, straight distribution, uniform distribution of charge along a straight wire, that electric field radiates along the planar radius direction. A closer spacing of field lines means a larger field magnitude. If the density of the field lines is heavy, then if the magnitude is of the electric field is assumed to be large. The field lines never cross. Field line never cross. Field lines never break. Never break. It is always assumed to be continuous. At every point around the positively charged sphere, electric field vector points radially out of the sphere. Sphere, radial direction. The density of the field lines is proportional to the strength of the field. It's redundant. It is already explained above. The density of the field lines, okay. The number of field lines should be the same for any charge of the same amount. Yes. Plus 1 Coulomb, 2 Coulomb. Then field line. If you draw 4 field lines, there should be 8, something like that. Electric field due to a monopole. This is electrostatic force between the charge Q and test charge Q0. If we remove this Q0 by dividing both sides by Q0, then you obtain the electric field. If you choose the origin to be the place where this source charge Q is placed, then this R is the distance, and we can draw a sphere. The radius of the sphere is R. The ER hat, this is a unit vector along this direction. Therefore, the electric field radiates if the source charge Q is positive. If G is negative, the direction will be flipped. As you can see, the magnitude of the test charge has cancelled already, so magnitude of the electric field is independent of the test charge. The direction of the electric field is independent of the sign of the test charge. Sure, it is independent of Q0. We don't care about the test charge's sign and magnitude. Superposition of electric fields. If you put many charges as source charges, the contribution of every charge, they are to be added algebraically as a vector sum. Q0 is the test charge. If there is a test charge Q0 and there are Q1, Q2 through Qn, then the net electric field applied to this field point. And there are various source points. Electric field at a single field point is to be computed by summing all of the Coulomb forces between Q0 and any one of the charge distribution. At the end of the day, we divide both sides by the test charge Q0. Then you will find that the net electric field is the sum of the vector sum of the electric fields due to every charge. Let us consider one-dimensional charge distribution. Linear charge density lambda is defined by lambda. Okay, so we assume, for simplistic case, the uniform charge distribution on some geometrical object. First, straight wire with uniform charge distribution. That means per unit length, we assume dq is placed. The ratio charge divided by the length of the line segment on which the charge is distributed is assumed to be constant when it is uniform. Surface charge density. If we consider a plate that is charged with electric charge in a uniform way, then the ratio of the charge divided by the area of a small patch should be a constant. We denote this one by sigma. What happens if you have a distribution of charge over a volume? Then we use a special notation, rho, that is the charge divided by the volume. We compute the electric field due to a uniform circular charge distribution. We have a capital Q distributed over a circle of radius r on the xy plane with radius r. Okay, so this is the distribution of source. So charge Q is distributed over this region. What is the density? Density of the charge is a linear length. It is circumference of the circle is 2 pi r, and the net charge is small q instead of capital Q. In that case, Q divided by 2 pi r will be the linear charge density of this distribution over a uniform circle. A differential element of the charge dq, how much amount of charge is in a small arc length, ds, if we can introduce azimuthal angle measured with respect to the x-axis, this is phi, azimuthal angle, and another point has a phi plus the d phi. Then the differential of the angle is d phi. Because the radius of this circle is capital R, the arc length is ds, that is r multiplied by d phi. If we substitute this one in here, this is a total charge. However, this ratio is a uniform, so divided by r d phi. From this, we can find that dq equals lambda multiplied by the arc length. This one should be substituted to the equation for Coulomb force formula, from which we can determine the electric field 1 over 4 pi epsilon 0 dq divided by radius squared, and use the unit vector along the radial direction. However, this radial direction does not mean the radial vector from the origin to a field point. Instead, it is generated by a small charge over a small line arc length. So, if we choose a field point somewhere around here, here we have chosen a field point P to be on a z-axis in here. So P is here and point Q is here, and the radial direction is along this direction from source to the field point. So the vector Q to P from Q to P is x. We have x comma y comma 0, and this point is a 0 comma 0 comma z. And from Q to P, that is a 0 0 z subtracted by x y 0. Therefore, we have minus x e1 minus y e2 and z e3. Using this parameterization of a cylindrical coordinate system, we find that z and x and y are expressed as like that. So substituting, we have a radius r, this is z, and each point, this is x and this is y. And this is the distance from the source to the field point. Using this expression, we can compute the unit vector. Previously, we used ER when the charge is at the origin. So in order to distinguish this one from ER hat, we introduced N hat. That is the vector from displacement vector from Q to P divided by its magnitude. Substitution of these numbers into this expression, we find that it is simply expressed like that. As a result, the differential electric field element due to the infinitesimal charge element at Q with an differential azimuthal angle d phi is like that. In here, we have made use of a simple expression x squared y squared should be r squared because it is on a radius on a circle of radius r. Finally, we can integrate this one over an azimuthal angle d phi. We find cosine, sine, azimuthal angle dependence completely disappears. And we end up with the z direction only. The integral over d phi is independent of polar angle theta, so this integral is trivial, that is 2 pi. The reason for vanishing contribution along the x and y axis is actually very simple. We can choose the same symmetric point opposite. In that case, this contribution of the electric field is in this direction. We can draw a cross-sectional plane and find that the contribution coming from Q prime, that is opposite side, that has a symmetric contribution to the electric field. However, this direction, they have a exact cancellation along this axis. Therefore, the only contribution survives is along the z-axis. So, even though we can make use of this integral table, before evaluating this integral, we already know the full angle, the integration over the full angle of the azimuthal angle will give only the z direction contribution only. As a result, the electric field due to a circular charge at a field point on the z-axis is expressed like that. When z goes to infinity, that means that z is much greater than r, then we can ignore this. What happens? In that case, this expression becomes z over z cubed, that is 1 over z squared. And when z is very large, in comparison with the radius of this circle, it is just like a point. If you look at a circle very far away from this circle, then you can see this is just like a point. So it is just like the electric field generated by a single point charge. Instead, if we approach this z to the origin, center of the circle, what happens? In that case, z is very, very tiny, and we can ignore z in that case, then it is frozen to a constant value. And at exactly the point as the center, because of the symmetry, all of the contribution are symmetric to have an exact zero value at z equals 0. Uniform charged disk also generates electric field, and that can be computed by making use of this result for the circular wire, because we can slice the disk into a very thin ring and vary this variable radius small r from 0 to capital R and sum them all. That is integration. So we just copy the previous result. For the case, we have a net charge Q is distributed over a wire of radius capital R. In here, we have variable radius small r. And we have charge dq instead of q. So carbon copy and then replace small q with dq, and that dq should be expressed as the surface charge density multiplied by the area. So we have changed the variable using introducing t, that is r squared, then the expression becomes quite compact. And we can make use of this integral table. If you do not understand the integral table, simple way is to take the derivative of the right hand side, whether you can reproduce the integrand. Using this integral table, we find that electric field generated by a uniform charged disk is like that. As you can see, when the radius r, capital R, goes to infinity, this one vanishes. And you will find the z over z absolute value. That means even though there is a discontinuity, when z is a positive, it is a sigma over 2 epsilon 0. And when z is negative, it is opposite direction. So uniform disk generates the electric field in opposite direction on each side. And this is a very important expression. You have to remember exactly. Electric dipole. Dipole moment. We define electric dipole moment P, that is charge Q multiplied by the distance. What is the electric dipole? Charge plus Q and the same but opposite charge minus Q are separated by the distance d, and this vector d has the direction from the negative charge to the positive charge. So we need to know the definition very well. The contribution of the electric field is 1 over r squared q 1 over 4 pi epsilon 0 er, something like that. The contribution of negative charge if they were at the same point, the net electric field must vanish. However, if they are separated in a finite distance, then the cancellation is not exact. However, at leading order in 1 over r, nth power, we have a very large distance, then the electric field, which satisfies the inverse scale law, cancels at leading order. And the subleading order, that is something like 1 over r cubed. To have the dimension the same as this, we have the distance scale, the separation of the two charges. This factor appears to be the leading order contribution of the electric dipole moment's electric field. And Taylor series expansion can be used to expand those contributions. And finally, contribution of the electric field due to the plus charge and the minus charge has a very similar shape. However, their sign, their subtraction, because it is a positive charge plus Q contribution and minus Q contribution at leading order in Z, that cancel exactly. This contribution cancel exactly, and in the difference, that subleading order contribution, what is delta? What is delta? What is delta? Delta is this one, z plus delta. 1/2 of d is assumed to be the delta. Therefore, if you add the two contributions, the electric field is not inversely proportional to the distance. Here z, charge q is at plus 1/2 of d, charge minus q is minus 1/2 of d, and this is the center, and the distance is d. You will find the electric field far away from this center is not following the inverse scale law. This is a 0, z point. Instead, it is proportional to 1 over distance q. So, electric field due to the electric dipole far away from the charge distribution is much, much weaker than the single charge distribution. Single charge is just a point charge. Point charge proportional to 1 over r squared. That is the inverse scale law. And dipole dynamics, if you have an electric dipole, then electric field on the external constant electric field, and this positive charge has the external force QE. Here, the negative charge accepts the electric field, so electrostatic force is opposite. The sum of the two forces, so net force to the electric dipole due to a constant electric field is 0. However, with respect to the center of this electric dipole, we find there is a non-vanishing torque. It makes it to rotate clockwise. This negative charge on the Coulomb force also wants to rotate this side. Therefore, finally, it has a torque along this direction. What happens if the angle is on the other side? In that case, force is like that. In that case, it wants to be along the counterclockwise direction. So, it is something like a pendulum. There is a stable equilibrium point and it would oscillate. Something like if you rotate this one in this way, and electric field is along this direction, and positive charge, negative charge at center, then this system wants to keep on oscillate with respect to the equilibrium direction. So we can compute the torque on a positive charge and negative charge. Both of them has the same contribution. So sum of the two contribution to the net torque is electric dipole moment. This is electric dipole moment multiplied by the electric field. It is not a simple multiplication, it is a cross product. As a result, you end up with this relation. It is very similar to what we have found in the previous semester for the pendulum motion. If you have a torque, something like that, then we can make use of the fact it is a conservative force. We can define the potential energy, the corresponding potential energy from this torque can be obtained proportional to cosine theta multiplied by the negative sign. In such a way, we can redefine this potential energy by subtracting the constant term that does not contribute to the actual equation of motion. So simply the potential energy of an electric dipole in a constant electric field E is minus P dot E. And the torque is P cross E. Okay, you can refer to a very interesting paper, our K-pop collaboration for the electrostatic potential of a uniformly charged triangle by making use of barycentric coordinates. You can click it to find what paper is. Okay, that's it.